So the homework from last day, page 214. I will be doing a homework check later on today or tomorrow for sure. I'll be checking lesson 1 and 2. Next class, yeah. Thank you, Captain Obvious. Any of these that you were wondering about, that you were going, holy schmoly, I cannot get these. Number 6? Ah. Any besides number 6? I heard, can I do number what? Oh, maybe I didn't hear anything. Yeah, that's why I'm here. Any others besides that? Okay. Adam, remember the average was, the mean was the average. The standard deviation was the spread, how spread out things were. Okay? So I'd like you to imagine that we took 10 guys and we set them up in order of height from biggest to smallest. Okay? The spread wouldn't be too big. What if we had them all standing on a 7-centimeter high platform so that they all increased their height by 7 centimeters? Would that change how spread out the heights were at all? It would change the average height, but it wouldn't change the spread. If you add the same thing to everything, all you're going to do is you're going to move the data, Liam, left and right, but you're not going to make it spread out more or spread out less. So it says, state the mean and the standard deviation if each data value is increased by 7. The mean would still be 15. The standard deviation would be the same, 3. Wouldn't change the spread. Does that make sense, Shania? If you add the same amount to everyone's test score, for example, I'm not going to change how spread out the test scores are. I'm just going to bump everyone's grade up by the same amount. But whoever got an F got bumped up by the same amount as whoever got an A. Make sense? Sorry? Oh, it means 22. It's 15 plus 7. Yeah, because you're adding 7 to everything, so everyone goes up by 7. Thank you, Matt. If you decrease the data by 5, the mean is going to go down to 10. But again, since you're doing the same thing to everyone, the spread is going to stay the same. Does that make sense, Taylor? Okay. All right. Really important, by the way, I just got a new wireless keyboard and I'm getting used to it, so my typing is going to be a bit wonky. Sierra, what I want you to realize is the standard deviation measures how spread out the data is. And if you add the same amount to everything, you're not going to change the spread at all. Okay? There's a great quote from George W. Bush. Okay? And this tells you how bad his math was. He said, "We want to raise the reading average so that all children are reading above the reading average." Wait a minute. If everyone becomes a better reader, doesn't that also move the average? Like, can you ever get every single person above the average? No! Half the people are below the average, half the people are above the average, and if you increase everybody, your average is going to increase. It was a dumb quote. Can't do it. Which tells you my opinion of him. Anyways, Devin just figured it out. Oh yeah, you can't get everybody above the average because half the people have to be below the average and half the people have to be above the average for it to be the average. But if you get everybody above the average, you've moved the average. That make sense? Okay. That leads us into lesson 3. Can you turn, please, to page 219? You're going to learn about an unknown distribution that rules your life. This is going to be the meat and potatoes of the unit. In other words, if you're lost after today, watch it again at home, come see me after school, do what you need to do. But if you don't get today, this is the foundation. After this, I'm going to be spending the next 5 lessons building on this foundation. We're going to talk about the normal distribution. We're going to talk about the mathematical definition of normal. There is a mathematical definition. Mom says I'm abnormal. No, Boston, we're talking about the mathematical definition. It has been discovered, observed, noticed, that many observations of physical measurements, such as length, volume, mass, time, etc., they all have common characteristics in how their data is spread out. For example, if you measure baby weights and you put them on a histogram, so the measure of newborn babies, measure their weights, most of them will weigh roughly the same. A few will be heavier, a few will be lighter. Does that make sense? Oh, an average assignment. Most of your homework assignments take the same amount. Here's your essays that take several days. Here's a take-home quiz. Most of your assignments, though, probably take, what, about 45 minutes to an hour. That would be the mean. Student heights. Most people are about the same heights. Here's Jordan. Actually, probably not quite that far. Probably Jordan's about here, because there are 7-footers and 7'2" people, bigger people. Here's Mitsu. Well, no, I shouldn't say that. Well, here's shorter people. They've noticed that there are a whole bunch of physical situations that seem to match what we call a bell-shaped curve. It says, draw a frequency polygon by connecting all the midpoints of the top of each bar with a smooth curve. Connect the dots. Connect the dots. That curve has a name. Do you notice all the curves look very similar, Marcus? We call this, the slang term is the bell-shaped curve, because it's shaped like what? A bell. Okay. If you've ever heard the term grading on the curve, this is the curve that they're talking about. All of your grade 10 provincial exams and your grade 11 socials exam are graded on this curve. What they're going to do is they're going to have 10,000 students, let's say, right, Joe? They're going to put all the scores on the curve. The middle is going to be the mean. Here's your A's, here's your B's, here's your C pluses, here's your C's, here's your D's, here's your F's. Here's the kids that get 100%. Here's the kids that write their name and walk away. This shows up all over the place. Anytime you have a reasonably big sample, it's going to match the normal curve. So data which results in a frequency polygon with a bell-shaped curve with this is said to be, underline this, normally distributed. It's that common. We actually say, this is normal. Are there abnormal well, there's other distributions that have different names. This is called the normal distribution curve, or the normal curve, or the bell curve, and it's widely used in making predictions in statistics, because if I know ahead of time, Emily, that my data should look like this, I can then start to predict, looking at only one piece of data, where it fits in on this curve. I can tell you, here's the magic phrase, how many deviations below or above the norm you are. Next page. Here's a concrete example. This is where you might use this in industry. A manufacturer who makes 100-watt light bulbs for Globe-Bright Incorporated is interested in determining the distribution of the lifetime of the bulbs. He wants to know how long before they burn out. He tests 44 bulbs. Now, in real life, if you're a manufacturer, Simon, you'd test maybe 500 or 1,000, but we don't want to have to type in all this data. So I will almost always give you small samples, but you can say, oh, I can see how they're going to apply it to industry. He tests 44, and he finds that the average, the mean, is about 900 hours. And he finds the standard deviation to be 50 hours. We know how we could calculate that. We could type all this into our calculator, or, Liam, we could do it by hand if we want to be like Boston. No, I converted you last class. You said it's nicer to use the technology. Okay. So he says the average is 900, the spread is 50. The mean and the standard deviation are approximately 950. So what he does is he creates a histogram. He says, you know what? The number of bulbs that lasted between 750 and 800 hours, only one of them, right there. Then he said there's a bunch of bulbs that lasted between 800 and 850. He went through, well, 1, 2, 3, 4, 5, 6 bulbs. Yoink, 6 bulbs lasted between 800 and 850 hours. He found 15 lasted there. 900 lasted, 15 lasted between 900 and 950 hours. And you'll notice it does take on that bell-shaped curve. Not blatantly, it's jagged, I realize. Oh, but if I sampled more, Danielle, I could probably smooth this out an awful lot. You okay with me so far? Okay. So we're going to use the histogram to create the following table. By the way, this would be a bulb that lasted a long time. This one's probably defective. How many bulbs were below 800? Yoink. 1. What percent of the bulbs were below 800? How many bulbs did he survey? Did he test? What did the question say? It's going to be 1 out of 44 times 100 to get the percentage. But I'm not going to write that. I'm just going to write the percentage in here. So we're going to go the number divided by 44 times 100. Got your calculators? Yes? Go to the run menu now, not the stat menu. So menu run. 1 divided by 44 times 100. What percent of the bulbs lasted less than 800 hours? 2.3. How many bulbs lasted between 800 and 850? 6. What percent is that? Can you go 6 divided by 44 times 100%? What'd you get, Courtney? Sorry? What percent is this? Can you go 6 divided by 44 times 100%? 6 bulbs is what percent of the bulbs? I have no idea what you said. 13 points, is that what you said? 13.6, is that right? Yeah. Don't bother typing this into your, don't bother trying to do this in your stats menu. We're going to find shortcuts. How many bulbs, Joe, lasted between 850 and 900? 15, what percent is that? Oh, you know what? He's got it right here in the next column over. 15 out of 44 is 34.09%. Because there was also 15 that lasted between 900 and 950. How many lasted between 950 and 1,000? 6 again, which Courtney said was 13.6%. How many bulbs lasted more than 1,000 hours? 1, which was 2.3%. It's these percentages that we're interested in. Because, say on your Math 10 provincial exam, or your Science 10 provincial exam, did you get a score back as a percentage? This is how they calculated the percentage. Part C says this. Using an average, a mean, and we're going to start, instead of using X bar, we're going to start to use this symbol, but you'll have to remember that your calculator uses X bar. Sorry, Jeremiah. And a standard deviation of 50. Write the following numbers in terms of that and that. Here's what I really want you to realize. What's the average, Raylin? What's the mean? What's the standard deviation? 950 then is the mean plus 1 standard deviation. It's 1 standard deviation more than the mean. If I wanted to use stat speak, you're 1 deviation removed from the average. 850 is the mean minus 1 standard deviation. You're 1 standard deviation below the average. And in stat speak, if you are within 1 standard deviation of the mean, you're considered normal. $800. You know what? 800 is the mean minus 2 standard deviations. It's 900 minus 100. But what we would really say in terms of stat speak, it's 2 standard deviations below the average. What about 1,050? That's above the mean. How many standard deviations above the mean is 1,050? 3. As an example, IQ tests. On an IQ test, the mean is 100. If you're one standard deviation above, which is 120, or one standard deviation below, which is 80, you're considered normal, anywhere between 80 and 120. If you're two standard deviations above, between 120 and 140, you're considered bright. Three standard deviations, anything over 140, that's the genius level. And you can apply for Mensa, which is the Society of Geniuses. That's how it works. So, pardon me? I usually test around 130, 135-ish. You know what it means? I'm smarter than the average bear. I'm smarter than a lot of the smart bears, but I'm not a freak. I have a friend who is brilliant, who leaves me in the dust. He has his engineering physics degree, and I can just tell, like, well, when he got his engineering physics degree, he was so highly sought after, he turned down the job where they offered him Albert Einstein's old office. Didn't want that. He had better job offers. Oh. Okay. No, it's just, but he's also hardworking. Okay. So he went to university, raised a family. He was working 8 hours every night, doing his studies 8 hours every day, and for about 2 years slept about 3 hours a day, and somehow managed to do it. I don't know how. It says complete the normal distribution curve based on the results for this example. So 34.09% are in this section, and I think it was 34.09% were in the 900 section, yes? I'm just reading from the chart on the previous page, yeah? What came after 950? What was the next measurement on the graph? 1,000?
Yeah.
Yeah? What percent were between 950 and 1,000? I don't have it on my page, but you have it on the you guys have it on the previous page. Jeremiah, what was it? Yeah, 13.6? 0.3? 0.6? 13.6, I think. Right, Courtney, or is he getting it from the previous chart? I don't have it on my page. And then we had 1,050, which was 12 point, sorry? 12 point? It was 2.3, right? Barely any made it that far. Oh, going in the other direction, we had 850, and we found 13.6% were there, and we had 800, 2.3. Yo. I have two 900s. Ah, dumb. Thank you, Liam. So it's 850, 800, 750. Moving down one standard deviation each time. We're going to use the standard deviation as our spread measurement. Thank you. If I wanted to write this as the number of standard deviations from the mean, this is 0 standard deviations from the mean. 1 above, 2 above, 3 above. You know what? I'll change colors so that stands out for you guys a bit more. 0, 2 above, 3 above. 1 below, how about I write that as a -1, Aaron? 2 below, 3 below. Is that okay so far, Sierra? Or I can write this purely algebraically. Now, we're going to find a way to do a lot of this with our technology, but to understand what's going on, you need to know you need to understand the math. I would say that this is the mean. This is the mean plus 2 of those. This is the mean plus 3 of those. This is the mean minus 1 of those. This is the mean minus 2 of those. And this is the mean minus 3 of those. So let's suppose I'm with the BC Ministry of Fisheries, and I want to preserve the smallest 90% of salmon. I only want to let fishermen catch the biggest 10%. I want the smaller ones to be able to continue to breed and continue to spawn. Okay? I would catch maybe 500 salmon. There's my sample. I would measure them all, type them in, I could get the mean and the standard deviation, yes? Then, using that, I can figure out how far over until I get 90% of them. Everything above that is the length that I'll allow to be caught this year. Everything below that, the fisheries rules this year will say, no catching those. You have to release them. So it's used all the time in conservation. It's used all over the place. The curve above is based on one example, and it's a good approximation to, here's the big one, the standard normal curve. Turn the page, page 222. Okay. As math nerds, we wanted to study this curve. So we wanted to have a standardized one. It's called the standard normal curve. And as math nerds, we said, you know what, let's pick nice numbers. What would be the nicest possible average? We said, you know what, how about 0? 0 is a nice average because I can do easy math with that. And I'm going to pick a spread, a standard deviation. That's also a nice number to do math with. What's the nicest number to do math with after 0? 1. The standard normal curve, as it turns out, has a mean value of 0 and a standard deviation of 1. We use a capital letter N for standard normal, comma, and then we write the mean and the standard deviation. In case you're wondering, because you're a nerd bender, what the equation is, as it turns out, the equation is this thing. If you graph that on a graphing calculator, you'll get a lovely bell shape. Now, we're not going to, Aaron, but look closely at this. What appears in this that should scare you a little bit or make you go, say, what? What do you see showing up in this equation? What symbol appears that you've seen before? Pi. Apparently, Liam, the way that heights are spread out among the human race, pi has something to do with that, and that should scare the heck out of you. I have no idea why that is. Or the way that your scores were spread out on last year's Math 10 exam, yeah, apparently pi has something to do with that. Really? Really? Oh, come on, that's a little weird. Says graph this and verify the shape. We're not going to, but if you're bored, you can try it later on. Says the terminology, blah, 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 and the equation are not required for this course. So we're going to scroll right to here. Here is the standard normal curve. The mean is dead center. Liam, what's the mean? 0. The mean of the data is 0. What are we going up by? What's the standard deviation? 1. And your calculator has this curve programmed into it. What percent of the data is above the mean? All those. Can you add those together on your calculator? Can you go 34.13 plus 13.59 plus 2.15 plus 0.13? Using the run menu, right? What percent of the data is above the mean? And the answer shouldn't surprise you. Sam, what'd you get? Oh, you didn't do it? No. You looked up. Marcus, what'd you get? Oh, okay. Joe, what'd you get? Exactly 50, yes? You know what? If in a proper curve, half of everybody is above the average, half of everybody is below the average. That's why it's the average. That's why I said that George Bush comment earlier. You can't bump everybody up. 50% is above the mean. Oh, and then what percent is below the mean? Also 50%. What percent of the data is within 1 standard deviation of the mean? Now, that means if you go 1 below and 1 above, what percent does that include? Add those two up, or just type in 1 times 2. What'd you get, Emily? What percent is within 1 standard deviation of the mean? No, that's only going in one direction. You have to go up or down. Double it. Did you add it in your head together twice? Thank you. I'm going to go 68.3. In fact, you know what? We're just going to say 68, but we are going to memorize that. But we'll do it pretty easily. 68, roughly. What percent of the data is within 2 standard deviations of the mean? Plus, 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 or plus, plus times 2. Liam. Oh, don't all rush for your calculators at once or anything. It's not like I paid good money so you could have those in front of you. Sorry? I think it's higher. 13.59 plus 34.13 equals, and then times 2. Isn't it 95.4? Yeah. What percent of the data is within 3 standard deviations of the mean? I think this one is 99.7, but double check me. That means you actually have to type stuff in and double it. And again, the easiest way, Joe, plus, plus, plus equals, and then double it, because it's going to be the same on this side, right? Only typing in 3 numbers, hitting enter, and then times 2. Is it 99.7? Yeah. In fact, we're going to call this a rule. We're going to call it the 68, 95, 99.7 rule. 68% of the population is within 1 standard deviation of the average. That's most of you. 95% of the population is within 2 standard deviations of the average. That's probably all of you. And then there are the outliers. We will find out later on with Jordan whether his height makes him in the 2nd standard deviation or the 3rd standard deviation. And I'm really interested in his shoe size. He's got big feet. Oh, what percent of the data is between 1 and 2 standard deviations above the mean? I can just read that. What percent of the data is between 1 and 2 standard deviations above the mean? 13.6. Same number that Courtney came up with when we did it by hand. What percent of the data is between 1 and 2 standard deviations below the mean? Also 13.6. So far, so good? Yeah. Turn the page. Here are the properties of the standard normal distribution curve. First of all, the total area under the curve is 1, or 100%, because 1 as a percentage is 100. That's how we can turn this into percentages. The normal curve extends infinitely to the left and to the right. It actually keeps going forever and ever. It assumes that it's possible for somebody to be 1,000 feet tall, even though we know that's not true. It takes into account the possibility. It assumes that it's possible, Jeremiah, for somebody to be this tall, even though we know it's not true. It's going to take that into account, just in case. It's symmetrical about the mean. In other words, 50% of the area is to the left, and 50% of the area is to the right. All the data is represented by the area under the curve. Oh, and not only that, Johnson, the mean and the median and the mode are all the same value. They're all 0. We set it up that way on purpose, Joe. That funky equation with the pi in it, that's what gives us this. So, how might you use this? Oh, hospitals. A nurse records the number of hours an infant sleeps during a day. He then records the data on a normal distribution curve shown below. So some researchers take 100 babies or whatever, they measure how many hours they sleep a day when they're newborns, and they graph them. Look at this curve. What's the mean? Boston, you said it. Oh, Matt, 12. Average baby sleeps 12 hours a day according to this data. Can you figure out by looking at the values on the x-axis, what's the standard deviation? 2. So when they typed in all the data, this is what their calculator spat back at them. So let's see if we can fill out the values for A, B, C, and D. What would go where the C is here? 16 and 18. What would go here? 8 and, okay. Here's your something maybe wonky ADHD or some other health problem. Here's your something wrong with this. We need to look and find out what's going on. Here is normal. The average baby. Oh, no, I can't. I want to say average because that's me. Normal. You're within the norm. D. What percentage of days to the nearest hundredth does the infant sleep between 12 and 14 hours? What area is this right here? You may have to turn back up. Do you have the, is the chart still on the same page? Is it? Yeah, you got the chart there? Okay. You would expect for 34% of the days, your baby sleeps between 12 and 14 hours. What about between 8 and 16? What percent? $95? Point. What about less than 6 hours? Point one, is it 0.13% or 0.13%? Sorry?
0.13.
So almost no infants sleep less than 6 hours. If they do, like this is how a doctor would say, this is not normal, we got to take this kid in and put him under observation, and they're going to the ICU. And this is nice for new mothers. They're saying, hey, my kid's sleeping 15 hours a day. You know what? A fair number still do. My child's only sleeping 7 hours a day. Contact your doctor. My child's sleeping 9 hours a day. You know what? That's still pretty close to the norm. Don't freak out, but watch your child. Keep an eye on him. Problem. Why at this time can't we figure out the percentage for sleeping less than 13 hours? Right there. Why can't we do that? We don't have any percentages to go with right there. Yet. Not yet. Okay? Next page. So what mathematicians have done is they have created something called z-scores. Told you, this is the meat and potatoes. We're going to learn a lot today. We have created something called z-scores. It's not possible with the given curve in example 1 to determine the percentage of days for 13 hours because the model of the curve is limited to integer values of standard deviations from the mean. We can only go 1 standard deviation, 2 standard deviations. What if we want to go 1.3 standard deviations above the mean and find the percentage that is? Or negative 1.3 standard deviations below the mean and find out what percentage that is. The concept of z-scores can be used to determine this percentage. A z-score for a particular data value is the number of standard deviations the data value is above or below the mean. Ready? We're going to see if we can derive it. The data value 18 is how many standard deviations above the mean? 1, 2, 3. So it has a z-score of 3. The data value 8 is how many standard deviations below the mean? It is a z-score of -2. That's how we say below. Negative, which makes sense. The data value 12 is how many standard deviations away from the mean? 0. So it would have a z-score of, I feel like, 0. All right. 13 is how many standard deviations. First of all, is it above the mean or below the mean? Let's write the word above here. What was the standard deviation on this graph? 2. How far above are we? What fraction of the standard deviation of 2 is 1? It's a half a standard deviation above the mean. It has a z-score of 0.5. Is that okay so far? It says complete the rows below the normal curve. Okay. This is the mean minus 1, 2, 3 standard deviations. This is the mean plus 3 standard deviations. This would be the mean minus 2 standard deviations. This would be the mean plus 2 standard deviations. Here's the mean. This has a z-score of -3. This is a z-score of +3. This is a z-score of 0. We're not going to fill in every one because it's going to get too cluttered. How can the z-score for a data value of 13 be determined? Well, we know the answer. We said the z-score is supposed to be what? Okay. Here's how you can get the z-score for a data value. Take your data, subtract the mean from it, divide by the standard deviation. That's the fancy schmancy notation. Show you how it works. The data value they gave us, Liam, here is what? Minus, what was the mean from this graph? Divided by, what's the standard deviation from this graph, Liam? Does that work out to 0.5? No calculator. What's 13 take away 12, Liam? 1 divided by 2 is 1/2, or as a decimal, 0.5. It works. Now you're going to use your calculator for more complicated ones. But this is the z-score equation. I will give this to you. You don't have to memorize it, but most of you will because you get tired of looking it up. Next page. There it is. You want to calculate a z-score, Jordan? You can find the z-score by taking the actual data value that you're interested in minus the mean. Oh, Matt, how many numbers are there here? 2. Make sure you hit put brackets or hit equals, and then divide by the standard deviation. A z-score indicates the number of standard deviations the data value lies from the mean. Positive means above. Negative means below. Okay. Nearly done. We're learning an awful lot today. This is the foundational lesson. So it says complete the following. Approximately 68.3 of the data lies between z equals what and z equals what? There's approximately 68.3 of the data lies between z equals what and z equals what? -1, and +1. Right? 95.4% of the data lies between z equals -2 and +2. Oh, Adam? Z! 99.7 is between -3 and +3. So let's put everything together here. Am I going to get through this whole lesson? A half hour left, Mr. Dueck. Give me a second here. Let me see how much of this I can get through. Okay, let's keep going. Okay. So you got your calculators out. Page 226, example 3, it says this. The heights in centimeters of 5 starting members of the Wolfhounds basketball team are 170, 182, 193, 195, and 212 centimeters. If the mean height is 190 and the standard deviation is 15, find the z-score for the tallest player. Here's the shortest player. So let's find the z-score for the tallest player. How tall is the tallest player, Aaron? So I'll write Z with a little subscripted 212. That's how I'll, because we're going to be using the letter Z over and over and over. But if I put the data as a little subscript, I'll know which one it came from. And it's equal to x minus mu all over the standard deviation, where x is the data value, 212, minus mu is the symbol for mean, average. What's the mean according to this question? Sorry, it says 190 divided by, and Joe, what's it say the standard deviation is? 15. This player would have a z-score of what? Okay, now I got to go to my run menu if I haven't already. Bracket 212 minus 190 divided by 15. 1.47. The fact that it's positive, Danielle, tells you he's taller than average. Oh, and I can be more specific than that. 1.4, be right about here. He's taller than about 30 plus 30 plus 13 plus 13 plus half of, I mean, he's taller than about 75% of the population. I will be more specific than that in a second, but he's pretty tall. One way they use z-scores, Sam, is to compare different types of data. For example, most of you wrote your Science 10 exam last year. Most of you did, your provincial. How do you know that exam wasn't tougher or easier than the year before, or this year's? Like how can we put on your transcript an exam score and compare it to somebody who wrote a completely different exam? You know what the answer is, Boston? Z-scores, Boston? Really? Z-scores. We're in Canada. We're proud Canadians. Z-scores. Okay. So, Tony wrote 3 exams. He got a 74, a 79, and a 68. So at first you may think, oh, physics, 68, that's his worst class. But here's the class average and the standard deviation. Let's actually find his z-scores, because whichever z-score is the biggest, that's his best class. Whichever z-score is the worst, that's his worst class, because that's comparing him to everybody else in that class. That takes into account, Emily, if that class is tougher or easier. It removes the level of difficulty of the class from the equation. So let's find, first of all, the z for math. Jordan, what did Tony get in math as a percentage? minus, what's the mean in math? Divided by the standard deviation is 12. What's his math z-score? .5. He's half a standard deviation above the class average. Let's find his z-score in chemistry. Okay. Emily, in the back row. What's his data value? What's his actual chem score? What did he get? 79, which looks like it's his best score, minus what was the class average? 73, divided by what was the standard deviation? Is that actually his best score? Ah, 0.43. He technically did better in math than in chem, even though he got a higher percentage in chem. Apparently that course is easier, because kids had a higher average and a smaller spread, or a bigger spread. Let's check out the physics one. 68 minus 66 divided by 11. Ooh, 0.18? Is that right? You get the same thing as me or not? Yep. He was barely above the class average in physics. He didn't do great at all compared to the rest of the kids. And now we can compare three completely different classes with different levels of difficulty. As long as we have the mean and the standard deviation, we can compare it to the rest of the population. Very nice. Okay. That's example 5, example 6, example 7. I'm going to come back to 5 and 6 and 7 in a second. For now, I'm going to pause here. Question 5, 6, yep. Can you give me like 2 more minutes? Okay. Homework number 1, 2, 3, 4, 10, 11, and I'm going to pause there. Emily, yes, you may.